much, Andrea. Ladies and gentlemen, first of all, I would like to thank the organizers for inviting me. It's a great honor for me. And I would like to focus today more on the variable amplitude loading, because we have heard the last 2 days a lot of very high cycle fatigue behavior, so I would like to focus on this behavior. After a short introduction, firstly, I would like to explain a little bit our experimental setup before I then present our results in terms of the mean stress effect, influence of repeated two-step block loadings, as well as the influence of low time histories. Moreover, I will show you a determination of a mean fatigue crack growth rate within the fish eye before I then conclude my lecture. In many fields of application, components and structures, like shown here, the helicopter rotor, wind turbine shafts, or the wheel side axles, but also medical products like stents are exposed in very high cycle fatigue, very high long life. And that means we have lifetimes that are more than 10 to the power of 9 cycles. So we have to be aware about the safe dimensioning of components and structures for the whole lifetime, because the defined fatigue strength, the conventional fatigue strength, which was defined by Böhler, is not very valid in the very high cycle fatigue regime. It can be, in this time, as it is shown here, like a duplex SN curve or double SN curve, how it is called, which is combined with a switch of the initiation side from the surface to the subsurface initiation, starting from an inclusion with a typical fisheye friction. But also continuous SN curves are observable. However, these are constant amplitude loadings. So components and structures are exposed to variable amplitude loading, like it should be considered here. So a lot of questions arise in this subject. What is with the mean stress influence in the very high cycle fatigue regime? What is, or do amplitudes below the fatigue strengths contribute to the damage? Is there an influence of variable amplitude loading on the crack initiation and possibly on the crack initiation site and the crack growth in the very high cycle fatigue regime? Have we interaction effects due to this very high cycle fatigue regime in the short crack growth rate? And can we explain this with plasticity-induced crack closure, although we are in the linear elastic regime? So first I would like to show you our experimental setup, and it is an ultrasonic fatigue testing system which has been developed at the Vienna. And because Professor Stanzel-Jack already showed this experimental setup, I would like to show you only some points of our experimental setup. At first, we have also a load frame in order to have the possibilities for different variable mean stresses. Moreover, we apply a pulse pause sequence in order to avoid the heating of the specimen. But we also cool, of course, the specimen with a fan. But just at the problem of variable amplitude loading, we have to adapt this pulse pause sequence, because the damping of the material is different for variable amplitude loading. So we measure the temperature at the surface of the specimen, and then we adapt this pulse pause sequence with our own software, Ufertest Valve. With this software, it is also possible to do experiments completely automatic under variable amplitude loading. So we used high-strength steel, 34 chrome nickel molybdenum steel, in the quench and tempered condition. It's wheel-set axle steel. We used for an R ratio of -1 this kind of hourglass-shaped specimen with a minimum diameter of 4 millimeters. And for all the other R ratios, we use this type of specimen in order to connect the specimen here with the counter bearing of our load frame. let us look for the mean stress effect, and here are shown the SN curves for different R ratios. The red dots show the R ratio of -1. You can see it is a continuous SN curve. We have no double-shaped double SN curve. And we have, for instance, here the green dots are showing the R ratio of 0. You can see that there's a large decrease of the fatigue strength. But what we also can see is that with an increasing R ratio, the number of cycles to failure increase. That means we have, for an R ratio of 0, a lot of failure above 10 to the power of 8 cycles, in contrast to that of the R ratio of -1. This is also presented by other researchers like Professor Beck and Kovac. And we also have performed fatigue strength experiments with a staircase method, and therefore we defined a limit number of 10 to the power of 9 cycles. And here you can see the results, and we can calculate it with these results, the mean stress effect of 0.52. If we compare this with the classical or conventional fatigue strength, you can see that there's nearly no difference between the conventional fatigue strength and the fatigue strength in the very high cycle fatigue regime. But there is a large difference at R of 0. This can be explained by the large number of cycles above 10 to the power of 8 cycles, because this would be assessed in the conventional fatigue stress determination as run-out. So we have there a clearly dependence. And also you can see that the mean stress effect of 0.32 for a conventional fatigue strength determination is increased in the very high cycle fatigue regime. To summarize this, I use the Hay diagram, and here the mean values of our experiments are given. And we would like to describe this, and we apply the Goodman relation and the Gerber parabola. And you can see for the investigated negative R ratios, it describes this very well. But these relations do not map the other R ratios. This has also been shown by Professor Sakai. So we applied the German approach of the FKM guideline, but used at first the mean stress effect for the conventional fatigue strength determination, and you can see these 3 lines that they do not map very well the experimental data. So we applied this with a very high cycle fatigue mean stress effect, and it maps very well, although we only use R -1 and 0, and all the others are in good agreement. Moreover, we investigated the fracture surfaces and measured the inclusion sizes in terms of the square root of area. This is area projected on the plane perpendicular to the maximum principal stress. What you can see is that we have mainly, as I mentioned before, interior failure starting at inclusions, and only 3 inclusions or surface defects. If we compare this with the other R ratios, especially with R of 0, you can see that for the R ratio 0, there's a large scattering, and the mean value of the square root of area is larger than that of R ratio of -1. In order to take this into account, we applied the square root area approach of Murakami, who calculated the stress intensity factors for subsurface and surface cracks, and he combined this with the threshold value for short cracks for square root of area smaller than 1,000 micrometers, which depends on the Vickers hardness, and we then can calculate it through the combination the threshold stress at which a crack initiation can take place. And that depends on if it is a subsurface or a surface defect. Moreover, here you can see that there is an influencing factor for the mean stress in terms of the R ratio, and the exponent alpha is also given by Murakami depending on the Vickers hardness. In our experimental work, we have adapted this and we used our own alpha parameter, which has been calculated from our experimental results. And if we apply now this to the SN curve, you can see that it collapsed to one SN curve like it is shown here. So it is an influencing factor. Moreover, we calculated the cyclic stress intensity factor of the inclusions depending on the lifetime, and here you can see that for the inclusions in the interior of the specimen, the cyclic stress intensity factors are larger than that of the subsurface inclusions, but they are far below the threshold value of long cracks. If we compare this with an R ratio of 0, you can see that they are also sometimes below the threshold value for long cracks, but they are also nearby the threshold value, which is a clear difference to the R ratio of -1. We would like to explain these different mean stress effects, and we heard about this, that also fine granular areas are different in different mean stresses or R ratios. So we decided to do an elastic plastic finite element simulation, and these are the first results we have got. So we used our specimen with an inclusion, and then we applied elastic plastic material behavior using the ONO1 criterion. We have performed the experiments and identified the parameters, and then we have done an elastic plastic fatigue crack growth simulation starting from an inclusion or a cavity. And surrounding this cavity or the inclusion, we have an annular crack with different crack lengths. For instance, here 15 micrometers. And with the node release approach, we propagate the crack with a crack length increment of 0.5 micrometers and determine the threshold stress in that term that we have changed from compressive to tensile stresses at the crack front. And here the first result, and I have to mention that we have applied a stress amplitude which is equal to that of the fatigue strength for each R ratio. And you can see that here for an R ratio of -1, there is a large crack closure event, and for an R ratio of 0.5 there is no crack closure because the effective R ratio is the same as the applied R ratio. And we also have shown here the comparison with the analytical solution of Newman, and you can see that it's it fits our results very well. Only in this case for an R ratio of -1 and here for R of 0, there's a little bit difference. So these are first hint for us to go further with these results to explain these mean stress effects. In order to calculate if small amplitudes do contribute to the damage, we have done repeated two-step loadings, like it is shown here. The small amplitudes are 10% below the fatigue strength, which has been determined in the very high cycle fatigue regime. And the high block is 10% and 20% respectively above the fatigue strength. The number of cycles in the high block are constant with 10 to the power 4 cycles, and the small amplitudes are varied in length. The cycle numbers are varied. And this is defined by the block length ratio with 1, 10, and 100 we investigated, and the block loading ratio is defined as here shown, and it is approximately 1.2 and 1.3. Here are the results of these repeated two-step loadings. Here on the scale you can see the block length ratio, and on this axis you see the number of cycles to failure. And depending on the block loading ratio which is applied or which can be seen here, Below the block length ratio of 10, there is nearly no influence of the block loading ratio, and also nearly no influence between 1 and 10 block length ratio. It means for 1 we have the same number of cycles in each block. But if this is increased, that means we have a lot of small amplitudes below the fatigue strength. The number of cycles to failure increase as we expected. But there is a difference between the block loading ratio. So we use these results in order to assess this with the damaged roots, with primary and minor roots, different ones. First of all, the primary and minor root in the original form, that means only the amplitudes above the fatigue strengths are considered. Then the elementary type, all amplitudes are taken into account. The same for the modified type by Heibach, with a different slope in the very high cycle fatigue regime, and also the Manuela Sander approach, where the SN curve is rotated around the highest cycle amplitude. And the slope is the mean value of the slope of the SN curve and the Paris exponent. We use this to calculate the lifetime, in that term that we have a damage sum for one cumulative frequency distribution for one sequence, and then we assume a theoretical damage sum of 1, and then we can calculate the number of cycles to failure for several sequences. Here the results in terms of the number of cycles to failure, which we calculated over the experimentally determined number of cycles to failure. And you also can see here the probability of survival of the experimental data. And what you can see is that for the same number of cycles in the high and in the low block loading, then you have nearly no difference of the different primary minor roots. But this is increased with an increasing number of cycles within the low block. And also you can see that the primary minor rule in the original type is within the scatter band and only slightly overestimates the calculated number of cycles. So this is a hint for that the amplitudes below the damage do not contribute or do not a lot contribute to the damage. But if we look for a higher block loading ratio, you can see again the difference for the same number of cycles is very small, but with an increasing block length ratio, the results, the number of cycles to failure, which we calculated with the original primary minor rule, progressively increase. That means we overestimate the number of cycles, and so we have to consider all the amplitudes, or we have to consider with some concept, the amplitudes below the fatigue strength. For the investigation of the load time histories, we use two types of standardized load spectra. The first one is the helicopter rotor spectrum Felix, which has been transformed for an R ratio of -1. And then we counted this with the rain flow method, and then we get such blocks within a restricted number of cycles in each block in order to have the block loading sequence for the ultrasonic fatigue testing system. Moreover, we have the wind turbine load spectrum called Whisper with a smaller number of cycles, and this is transformed to an R ratio of 0. First, I would like to show you the results for Felix, and because we have the problems to reconstruct now the sequence into a sequence, we have performed very simple reconstruction times at first. We have used the smallest amplitude at first and end with the highest, and vice versa, and we have a mixture. And moreover, we have different values of the maximum amplitude for the Felix 10 spectrum with 641 megapascals and 705 megapascals. And here you also can see the modified version of the SN curves, here for constant R ratio of -1 for constant amplitude loading, and the results of the variable amplitude loadings are shifted to higher lifetimes as we expected it. But what you also can see is that there is nearly no difference between the reconstruction types. But if we look for the inclusion sizes, you can see that there is a clearly difference between Felix 10 with a smaller, highest amplitude and Felix 10 with 705 megapascals. There are smaller inclusion types for the same number of cycles to failure. And here a small difference can be observed for the different reconstruction types. Nevertheless, all are shifted to higher lifetimes. Here we also have applied these damage rules, different primary minor rules, and also here you can see that the original primary minor rule leads to non-conservative results. That means we have to consider the amplitudes below the fatigue strength. The number of cycles which we calculate are the same because we have no interaction effects here in these calculations. And we also have very good agreement with the modified and elementary type. For the Whisper spectrum, here you can see that again the SN curve is shifted to higher values. I forgot to mention that also for the Felix spectrum, most of the amplitudes are below the fatigue strength. And in this case, we have 88.6 to 92.6, depending on the load amplitude level, are below the fatigue strength. So we have a very high cycle fatigue regime. And you can see it is shifted to higher values of the lifetime. But if we look for the inclusion sizes, it's just vice versa. The inclusion sizes are smaller of that of the constant amplitude loading. And if we now use the approach of Murakami, this collapses to one SN curve, one modified SN curve. We have no explanation for that at the moment. We assume that it should be, or it could be that the number of cycles are very near, or the amplitudes and the classes are very near to the constant amplitude loading. For the determination of the fatigue crack growth rate within the fish eye, we have to consider the surfaces. At first here the constant amplitude loading with a typical fish eye fracture and the inclusion in the middle. And if we look for the two-step block loading sequence, we have again the inclusion in the middle and we have the boundary of the fish eye, but I hope you can see here we have arrest marks, which are different in spacing and also different in the region where it exists. If we look for the load spectrum, you can see here again the inclusion size and the boundary of the fish eye, and within the fish eye surrounding this inclusion we have these arrest marks. So we have following assumption that we can calculate mean value of the fatigue crack growth rate in that way that we use the difference between these both, between the arrest marks, and this arrest mark is existent after one sequence of this variable amplitude loading. So we have a mean value of the crack growth increment divided by the number of cycles. And also we can calculate a mean cyclic stress value by the mean value of the average cycle of the cyclic stress weighted with the number of cycles within each class. And if we do this, you can see these fatigue crack growth rate, which are below the long crack growth behavior, which is shown here with a solid black line. In order to describe this, and then I will finish also, we applied two approaches. One is the approach by Shiozawa, and he said 90% of the lifetime is spent for the building of the fish eye. And so if we use this Paris law, we calculate or integrate this and can calculate this formula, and we have to determine the C and the M. And this is done using the own experimental data, using the cyclic stress intensity factor of the inclusion over the number of cycles to failure divided by the square root of area, and then we can calculate these parameters C and M. Moreover, we applied the formal approach, where the short crack growth behavior is taken into account with a threshold value, and we inserted here the inclusion sizes. And here you can see this dependence on the R ratio, but I would like to focus on this now. For the formal equation, you can see this short crack growth behavior. The Shiotsava approach shows this behavior with a calculated C and M parameter. This is not in very good agreement with our experimental results, so we decided to do following, that we did determine the Paris experiment and Paris parameter with our data using a regression line and apply this for the calculation of the remaining lifetime using the NASPER code. And then we can calculate it using this, the constant amplitude loading for an R ratio of -1. Here you can see the line, the horizontal line. This shows the results for the formal equation. So we have determined fatigue strength. That's not the case because we have here the results. If we apply the Shiotsava approach, it is shifted to the non-conservative side, but the slope is very well, but that's what we expect because we have determined the slope with this. And if we apply our regression line, you can see that it is also shifted to the right and the slope is not very well, but this is a hint that we have interaction effects which are not considered in our residual lifetime calculations so far. So let me conclude my lectures. The mean stress effect is increased in the very high cycle fatigue regime. Low amplitudes beneath the fatigue strength contribute to the fatigue damage in the combination of block loading ratio and block loading length ratio. The SN curve or variable amplitude loadings are shifted to higher number of cycles to failure, and due to variable amplitude loadings, arrest marks occur due to interaction effects, which can be used for calculating mean fatigue crack growth rates within the fish eye. At the end, I would like to thank the German Research Foundation for funding this research work. I would like to thank all the colleagues within this program, in this priority program, for the valuable discussion, and also Professor Staatschek and Professor Meyer for the discussions. And I would like to thank you for your kind attention.
Presentation. We are a bit late, but maybe we have time for one question.
Thank you very much for the nice presentation. Could it be possible that when we have high cycle fatigue, there is some sort of self-healing of the material at the end that increase the... Yeah.
Self-healing of the material, I didn't get it.
Could it be possible that some sort of self-healing is happening there, that you see a different behavior on the fatigue curve?
It could be some results show this, not from our group, but some research work show that there is a connection again between the boundaries, so it could be, but I cannot tell this because we have not investigated in detail this self-healing process.
Okay, thank you.
Okay, thank you. So